Hi everyone. My name is Ben Hudson. I'm a systems and ADCS engineer at KISPE, and I'm working on the open source satellite program. And today I wanted to discuss a presentation that I recently gave at the International Astronautical Congress held in Milan this year. And this is about an autonomous ADCS, so that's attitude determination and control system, an autonomous ADCS commissioning sequence for nadir pointing small satellites. And the idea here is this is applicable to our next generation microsatellite platform that we're developing, which forms a core part of the open source satellite program. So, as has been discussed before on the OSSAT podcast, KISPE has identified this gap in the market for a highly performant but low-cost small satellite platform. And this is because from our experience with some customer programs, we're finding that CubeSats are increasing in size, but often our customers are suffering from fundamental issues related to the CubeSat standard, the form factor, and sometimes the lack of performance being offered by those. But we also see that small satellites are trying to come down in price to get closer to that of the CubeSats, but are sometimes struggling to do so with their heritage designs and processes. And this is where the NGMP comes in. So the NGMP and the open source satellite, once it is released, will be a highly performant small satellite platform that is closer to the price point of a CubeSat, filling this market need that we have identified and have seen through many customer programs who are driven to the use of CubeSats primarily because of cost and not because of what is what they actually need. So the aim of the NGMP is to significantly reduce the price point of the platform through minimizing things like non-recurrent engineering, touch time of the system during integration and test, and also operational costs. And we can do this because we are starting from a blank piece of paper and can take a more holistic approach to the design. And here you have some key a description of the key elements of the NGMP. So we have this integrated platform avionics, which is shown on the architecture on the right, which minimizes the change required between missions of different applications. So all of the core functionality of the satellite that doesn't need to change on a mission by mission basis is kept within this integrated platform avionics. And that means it's only the peripheral items that may need to change depending on the mission. And we're designing this IPA with the idea in mind that it must service a range of different applications for initially low Earth orbit satellites. And then some other approaches we're going to be taking to reducing the NRE and the overall cost of the program are things like performing automated testing in INT, as this will minimize the touch time required. On the left here, we have the sort of first generation specifications of this platform. So yeah, as you can see, we have this scalable mass range of 25 to 250 kilograms, scalable power provision. So the power system could be increased in size if required by the particular application being serviced. And importantly, this 5 to 7 year lifetime with single point failure tolerance. And as part of reducing the overall mission cost, we have this desire to automate as much of the operations as possible. Now, the launch and early orbit phase has been identified by us as a prime phase of the satellite's lifetime to automate. So as I've just said, the NGMP will be capable of servicing a wide range of applications. And in fact, most satellite applications do actually operate in low Earth orbit and also require a nadir pointing attitude for operation. And by nadir pointing here, I mean a spacecraft that is pointing one of its body axes towards the center of the Earth. And you'll find that most applications need this, whether it be Earth observation, communications, satellites, and lots of others. So although the NGMP will service this wide range of applications, there is no reason why a common launch and early orbit phase approach cannot be implemented if most of these spacecraft require a nadir pointing attitude during nominal operations. And the launch and early orbit phase has some varying definitions, but overall we are thinking about the time here between the satellite being deployed from the launch vehicle, where it will typically be placed in a random tumbling state, through to when it is finally into its nominal attitude and it's ready to begin perhaps finalizing commissioning of the spacecraft and then entering nominal operations. Now, there has been some discussion in literature and by some other organizations regarding automating their LEOP operations, but there are in fact very few descriptions of actually implemented solutions and on-orbit results. And we think this is probably because of both a protection of IP issue, which of course is what we're trying to overcome with the open source satellite program, but also a general difficulty and hesitance to change heritage solutions. If you have a design that already works or has worked in the past, why change it? But we think this can be This can prohibit real development and advancement in technology, and this is of course a problem we do not have as we are starting from this blank piece of paper. So it is certainly an aim of the Orbital Satellite Program that will be capable of a greater degree of autonomy than has perhaps been demonstrated in the past. Now, a large portion of the activities required in the launch and early orbit phase are related to the ADCS, so the Attitude Determination and Control System. So to constrain this initial problem, here we consider the autonomous commissioning flow just for the ADCS. This is an autonomous solution for getting us from a random tumble from the launch vehicle separation through to nadir pointing. So we're not yet considering the commissioning of the rest of the satellite or of a propulsion system or the payload itself, and we'll consider these things further down the line as the NGMP and the Orbital Satellite Program develops. So on screen here is a nice depiction of one of the operations we'll perform in the launch and early orbit phase, this detumbling phase where we go from this random tumble through to a more controlled spin. And we also have the objectives we're trying to meet with this autonomous commissioning flow. So we want to minimize the time from separation to nominal mission attitude, as any time spent in this phase is not going to be producing any income, any money for the or actually performing the useful application of the satellite. We want to minimize operator intervention required. The LEOP phase is typically very people intensive. It requires lots of communication with the ground, which can be expensive from an operator point of view, and also from just the time of people required to monitor the spacecraft and perform some of these commission activities on the ground. And we also want a deterministic and robust autonomy logic that places the system into a safe state in the event of a failure, as we don't want this autonomous solution to put us into a state where we cannot talk to the spacecraft, or it actually causes a failure in the process of trying to get through to nadir pointing. So our proposed commissioning flow is shown on screen here, and this performs all of the required calibrations, health checks of units, and mode transitions required to reach nadir pointing. So for this example, we consider a mission which is using a star tracker and gyroscope attitude determination method, as this is quite likely for our first mission. The primary activities in this numbered flow are require a lower level of autonomous logic, and I will run through these in the subsequent slides. But just to give a brief overview of this flow, it is fairly typical in the activities it performs, but the novel part of this is the autonomous piece. So what we have here is separation from the launch vehicle, entry into a random tumble, and then a standard detumbling of the spacecraft from this random tumble through to a more controlled Y-Thompson spin. We're then going to turn on our GPS receiver and achieve lock with the GNSS constellations, perform biasing of our reaction wheels, calibrate the magnetometer, initialize all the algorithms that we need to enter nadir pointing, and then we're finally ready to transition to nadir pointing. And as I said, we'll go through in more detail each of these major steps in the next few slides. And the important thing here is theoretically there is no operator intervention required, as we've removed the need for any information to be provided from the ground. And in terms of failure philosophy, so the NGMP will ultimately be capable of failing available. So there'll be some automated recovery implemented to recover from certain types of failure to make sure the system is ready to perform the next operation. And we're progressing the design of the system with this in mind. But for now, we're just going to consider a fail-safe strategy. And by this we mean if anything goes wrong aboard the spacecraft and we detect the failure, the whole spacecraft will be placed into a power and thermally safe random tumble, which means it is passively safe for a long period of time, which gives us adequate time to contact the spacecraft, figure out what's wrong, and then put it back into the operational mode. So basically, in this autonomous commissioning flow, if any of the autonomous checks fail after some period of time, we will put the spacecraft into this power and thermally safe random tumble. So we've simulated the proposed commissioning flow in our AOCS simulation environment, which is running on a PC. And the spacecraft is modeled as expected for the first mission. So we're looking at a roughly 50 kilo class spacecraft in a 500 kilometer sun synchronous orbit, which is a very commonly used orbit for Earth observation applications. So the diagram here very simply shows how our AOCS software is actually implemented on board the spacecraft. So we have this code-generated AOCS solution, which is running within this wider ADCS task. So the light blue piece is a actual model-based development of the AOCS algorithms, and then we use that to generate our flight software, which is running within this wider AOCS task, which handles the sort of communications and data handling elements of the AOCS, but also runs these FDIR, so the failure detection, isolation, and recovery. So this has allowed us to provide a preliminary demonstration of the viability of the proposed logic for this autonomous flow, and begin to evaluate how long it might take to go from launch vehicle separation through to nadir pointing. So we've modeled this in our simulation environment in a model-based format, and then all of the proposed autonomous logic is implemented as part of this AOCS task piece. So the AOCS has been configured here for a mission capable of achieving higher pointing accuracy, so sub 0.1 degrees, 3 sigma, and that is sufficient for a fairly high resolution Earth observation mission. And you can see some of the other hardware specifications that we've used for this simulation on the screen. So the first stage in our autonomous commissioning flow was this detumbling piece. So we're going from a random tumble through to a stable Y-Thompson spin. And a Y-Thompson spin is when the spacecraft is rotating end over end along its orbit with the Y-axis of the spacecraft pointed along the orbit normal, so perpendicular to the plane of the orbit. And this means that later on we are in a position for that pointing axis to be slowed down and pointed towards the center of the Earth. So here we've implemented a standard detumbling algorithm that's been used for many years in the space industry, but we have these numbers of our autonomous checks being performed over time, so that we turn on the magnetometers and magnetorquers, which are used to do this detumbling. We check that our angular rates are decreasing, and this is to capture the failure case where the magnetorquer polarity is incorrect. So that is either because the magnetorquers have been fitted in the wrong direction, or the polarity in software is incorrect, and this is actually quite a surprisingly common failure that's been seen in the past. So checking that the rates are decreasing just makes sure that our magnetorquers are not configured the wrong way around and are actually speeding up the spin of the spacecraft rather than slowing it down. We check that our angular velocity is approaching a Y-Thompson spin, and that the Y-axis is beginning to align with the orbit normal, and that our overall spin rate is coming down towards 1 degree per second, which is a nice speed to then transition to nadir pointing from. So you can see that each of our autonomous logics here has this timer associated with it. So if this times out, so if the transition takes too long, there'll be autonomous transition to a safe mode. And this just stops any infinite loops forming due to failures that we haven't detected. So the system doesn't just get stuck in one particular mode, which in theory, could put us in a state where we can talk to the spacecraft. And we would refine the sort of stop times of these timers with some more testing and refinement on orbit of what works for each of these given transitions. So the simulation on the right here shows detumbling from a magnitude sort of 2 degrees per second random tumble, which based on some of the separation systems we've been exploring and then the launch vehicle options is a fairly common random tumble rate for a system of this size. And we show detumbling from this 2 degrees per second tumble down to a 1 degree per second Y-Thompson in just under 3 hours, which is fairly quick. And the magnetorquers have been sized such that we do keep this detumbling time down to a minimum. And all the autonomous checks that have been shown on the left hand of the screen here have been passed successfully in our software. So we're now in this Y-Thompson state where we're tumbling end over end at about 1 degree per second. And here we propose turning on the GNSS receiver much earlier in the commissioning process than is perhaps normally done. And our GNSS receiver is going to receive signals from constellations like GPS, Galileo, and provide us an estimation of the position, velocity, and the time of the spacecraft, which we do need to progress this autonomous commissioning flow. So this is perhaps done earlier than is typically seen in commissioning flows, and that's because a key activity we want to move from the ground to space is calibration of the magnetometers. Now this requires knowledge of the spacecraft's position, which without uploading this information from the ground via something like a 2-line element, requires the GPS receiver to be turned on. We also need knowledge of the spacecraft's position to eventually point towards nadir, and we don't want to have to upload this from the ground because it requires a link session, which we're trying to minimize. So we turn on the GPS early on, but a challenge here is that we are in this tumbling state. so that we have selected a GPS receiver that can achieve a lock from a cold start in 60 seconds, as essentially we have a GPS antenna on the spacecraft, which is only getting around 180 seconds of space-facing time per revolution. As you can imagine, as it's tumbling end over end for half of that spin, the GPS receiver is pointed towards the Earth, and it's not going to be able to get a lock on the GPS or Galileo or Beidou constellations. But we've placed our antenna on this minor Z face to give us this few minutes of space-facing time each revolution. And we've simulated here this exact process, and that is sufficient time to get a lock on the constellation for the GNSS receiver to provide an initial estimation of the position and velocity of the spacecraft. And then we actually use that to initiate an onboard orbit propagator to continue providing these position estimations for the latter stages of the commissioning flow. And that's the scenario we have modeled here. And the accuracy of that onboard propagator is sufficient to finish off the autonomous sequence that is needed here to get us to a point where we have continuous GPS lock. So we have obviously reaction wheels on board our spacecraft, which are used to provide 3-axis control of the system and very accurate attitude control. And we need to bias these reaction wheels. And reaction wheel biasing is performed to increase the speed of the wheels such that they're not operating around 0 RPM very often during the mission, as reaction wheels can be quite prone to failure when operating in this low speed regime, and the actual control accuracy of the wheel is quite substantially reduced when operating at these very, very low speeds. And both operating in the low speed and crossing over 0 RPM, so going from like a clockwise to anti-clockwise spin and backwards, both of these factors can impact the wheel's lifetime. And because we're going for this 5 to 7 year lifetime of the spacecraft, we want to minimize any chance of failures occurring. So we bias the reaction wheels, and essentially this requires us to increase the speed of all 4 of our reaction wheels to a point where the system is still kept in this Y-Thompson spin, but that the magatorquers are also acting on the system to sort of balance out the total angular momentum so that these wheels can continue to operate at these high speeds for the rest of the mission. So during the ramp up of the wheels, you can see that our attitude is disturbed. So we have this graph on the right here showing the angular velocity of the spacecraft. So our 1 degree per second Y-Thompson spin is temporarily disturbed during this ramp up. Once we've reached the final wheel bias speeds, it begins to settle back down to this Y-Thompson state. And it takes around 3,000 seconds, so just under an hour, for the attitude to settle back down to a nice stable Y-Thompson spin. But now we've got our reaction wheels nicely biased so that when we do transition to nadir pointing, they won't be operating near 0. So as I said earlier, a key activity we want to move from the ground to the spacecraft is calibration of the magnetometer. So magnetometers measure the magnetic field of the Earth at the specific position of the spacecraft, and we can use this to actually estimate the attitude of the spacecraft in combination with other sensor inputs. Now, magnetometer measurements, as you can imagine, suffer from noise generated by other spacecraft systems, and this can be very difficult to calibrate for on the ground, as all the electronics on board our spacecraft will be generating their own magnetic fields. So as such, typically additional calibration is conducted on orbit by downloading magnetometer data and running something like the classic 2-step algorithm on the ground. And this allows us to calculate the calibration parameters for the magnetometer to begin to compensate for these onboard interferences of the magnetometer's measurements. So different to what is traditionally done, we've implemented this 2-step algorithm on board the spacecraft as part of our flight algorithms so that this calibration can be performed on orbit. The orbit propagator is used to provide position estimations for the magnetometer calibration, which is required, and we run an onboard magnetic field model of the Earth, and the combination of all this data is used to perform the calibration. And we do this at this stage because it is beneficial to have the system in a tumbling state when performing this operation. So we perform calibration after biasing our reaction wheels so that there is some compensation for the wheel's magnetic fields, as they can be a fairly large source of interference. We have a constant sort of residual moment of the spacecraft assumed, and we've demonstrated that we can achieve a decrease in measurement error of the magnetometer from around 3 to 0.5 microtesla within 1 orbit's worth of data. Now, for some NGMP missions, for some open source satellite missions, this won't be required, as the system will be primarily using star tracker gyroscope attitude determination, and the magnetometer will only be used for performing things like reaction wheel desaturation. But we want to use this common LEOP approach for all of our missions, and as such, for those spacecraft that are just using sun sensors and magnetometers to perform attitude determination, this level of calibration is sufficient to achieve sub 5 degrees control accuracy and eclipse, just using this sun sensor magnetometer determination method. So once the magnetometers have been calibrated, we turn on our star trackers and our star tracker and gyroscopes, and we can begin to initialize the attitude determination algorithms that we're going to need for nadir pointing. So a key algorithm that needs to be initialized is the extended Kalman filter, and this is very much the core of our ADCS, as it estimates the attitude and the angular velocity of the spacecraft given certain sensor inputs. Now, this EKF is starting from an unknown state, and it's going to take in these sensor inputs and estimate with those what the attitude of the spacecraft actually is. But we need this Kalman filter to be initialized and providing nice, accurate estimates of the spacecraft attitude before we try and actually point the spacecraft towards nadir. So what we've got here, as you can see, from an absolute unknown initial state, we have our Kalman filter converging to a very nice, stable situation within around 80 seconds. So this is successfully estimating any biases of the gyroscopes and the overall attitude state of the spacecraft. And this innovation parameter I've shown on the right is a traditional measure of the Kalman filter convergence. And you can see how it's coming down nicely towards zero over time. So the spacecraft is now ready to transition to nadir pointing. We have all the required units turned on, we have the algorithms initialized, and we have knowledge of where the spacecraft is in space as we've begun propagation of that orbit with our onboard algorithm. So another key challenge here, very similar to the GPS, is that our star tracker must be deep space facing during the transition to get an accurate lock on the stars and to keep providing attitude estimations. Now we're in this 1 degree per second tumbling state still. So again, we have this 180 seconds of space facing time before the star tracker suffers from being pointed at the Earth, from being blinded by the Earth. And this also means the star tracker must be capable of operating at 1 degree per second in terms of the slew rate of the system. So essentially this means that the star tracker must achieve a lock on the stars and the algorithms must converge within this 180-second window. Now, as shown on the previous slide, we have this convergence occurring in around 80 seconds once measurements are provided by the star tracker. And then the remaining time, this remaining 100 seconds that we have, should be sufficient for the star tracker to achieve lock on the stars and begin to provide a couple of attitude estimations. And it's important to note this doesn't need to be highly accurate yet, because we just need sufficient accuracy to get us to nadir pointing, and then the system control accuracy will begin to settle down. So once this convergence has happened, the positive z-axis, which is defined as our pointing axis in this simulation, needs to be pointed towards nadir. So once this positive z-axis is within 45 degrees of the nadir direction, we begin the transition to nadir pointing. So the system will now actuate the reaction wheels, and now they've been biased, they will not operate near zero, and will point this positive z-axis towards the ground. And then through this subsequent transition, the star tracker is kept deep space pointing, as is the GPS antenna. So we have both star tracker measurements and nice GPS position estimations as well. And you can see here that once we've initialized the algorithms, got the star tracker working, it takes around another 135 seconds for the spacecraft to settle down to the pointing requirement that we need for this particular example. So this graph here shows the absolute pointing error. So this is the difference in degrees between the actual pointing of the spacecraft and where we want it to be pointed. And we have this down at this nice 3 sigma level that would be sufficient for some Earth observation applications. So here we're just summarizing the breakdown of the commissioning sequence as a whole, and the total time to reach nadir for this particular example. So you'll also see in this list here, we've included these 60-second periods for powering on a given unit and performing some autonomous health checks of that unit on board the spacecraft. We've got this 5-minute post-separation wait period, as some launch vehicle providers have requirements on when you can begin operations after separation from them. And this 5-minute time should encapsulate or should envelope any of those requirements. So this does provide a fairly competitive and short commissioning time for the ADCS to get us to this nadir pointing attitude within 5.5 hours for this particular example. And some of this will be dependent on the initial tumbling rate of the spacecraft, the size of the system, the size of the magnetorque with respect to the spacecraft. But the other key thing here is that this is performed without any intervention from the ground. So from launch vehicle separation through to nadir pointing, the operators are not required on the ground. So the next time that people need to contact the spacecraft, it is already in this nice stable nadir pointing state, ready for the rest of the commissioning to take place. So from an ADCS perspective, we've finished developing our ADCS algorithms, and we're progressing to sort of our verification stage of those pieces of software. It is likely for the first mission of the open source satellite, we'll use a more manual approach to the commissioning flow, but we will then hopefully demonstrate some of these autonomous elements throughout the mission once we've gained confidence in our ability to transition from idle back to nadir pointing. And then it is the plan that such a flow as this will become the de facto standard for the NGMP and the open source satellites going forward in the future. And the key thing for this commissioning flow is we've designed it such that it is agnostic of the specific application being performed, the spacecraft mass, presuming that the actuators are sized accordingly, and it's suitable for low Earth orbit and perhaps even some low medium Earth orbit operations. And the applicability of this flow begins to break down when you can no longer use Magator because the Earth's magnetic field is getting too weak. And of course, here we've only considered the commissioning of the ADCS on its own. The next steps in developing this commissioning flow are to think about what other parts of the system need to have more autonomous operations to enable this to take place, what some of these autonomous unit health checks look like, and a wider investigation into the FDRR analysis of the system, as implementing autonomy such as this is not a straightforward activity to perform. But we do hope this means that in the future, spacecraft operations will become far more autonomous, and something like this is particularly impactful for deployment of multiple systems at one time, such as if you were developing a constellation. So thank you very much for coming along today and listening to what I had to say regarding our autonomous ADCS commissioning flow. I'm very happy to answer any questions if people want to get in touch with me regarding this proposal. And yes, we'll see you at the next OSSAT podcast. Thank you very much.